Okay, hi everyone, welcome to lecture 17. And now we're pivoting away from linear programs and semi-definite programs for a bit, because we're going to see a different computational model, right, which is online algorithms. Okay, so, and then the lecture is divided into two parts, two big parts. And in the first part, as usual, we're going to ask the question, why should we study online algorithms and what are online algorithms? And then we're also going to learn, okay, how should one analyze online algorithms, right? Because it's a different setting, so this requires different metrics to analyze how good your algorithms will be. And then we're going to see some basic examples, okay? And then in the second part of the lecture, we're going to see the example of paging and caching, okay, which is a pretty good instance of where online algorithms show up in practice. Okay, all right. So why should we study online algorithms, right? So it turns out that online algorithms are important for many applications, okay? And in particular, you should think of an online algorithm, okay, is when we need to make decisions right when we receive the information, okay? So this is kind of the intuition of the setup, and then we're gonna formalize it. Okay, so for instance, where does this happen, right? For example, in the stock market, right? Like you receive news about a company and then you have to make a decision whether you buy stock or you sell stock, right? So you can't just go, oh, number always goes up, right? Like you have to make some decisions. And these decisions, you cannot see into the future, like the consequences of this decision. So once you see this decision, you have to make once you see an information, you have to make a decision right away, right? So it's as if the input, like it's coming, right? But not all at once. And you still need to keep making decisions like without seeing the whole input, right? Okay, so we have applications in the stock market, and then we have like in dating, applications in skiing, applications in caching, as we're going to see, applications in machine learning, for example. This goes sometimes by, well, there's many instances, but one of them is regret minimization, and many more. Okay, so the setting is quite important. And here, as we're going to see, it doesn't make sense to say, oh, I want my algorithm to have a worst case analysis in the same way that we had a worst case analysis for our deterministic or randomized settings, right? And why is that? It's because it could be the case, okay, that for a particular online input that we cannot see all the way, right? It turns out that no algorithm will do well with respect to that input sequence. No algorithm. All the algorithms will fail really badly, right? And if that happens, then you could say, well, my worst case analysis for my algorithm is really terrible. But what you're forgetting is that in the online setting, one thing that we need to do, like that's kind of the intuition and the motivation for this setting, is that you need to make decisions right when we receive the information. So if all algorithms are bad, you want to try to find the least worst, right? Or at least like close to the best algorithm. Does that make sense? Because you have to make a decision. So having this worst case analysis, as we were seeing before, doesn't really make a lot of sense here. Okay, but what makes a lot of sense here is the competitive analysis. And what is a competitive analysis? What we're going to do is we're going to measure the performance of our algorithm against the best algorithm that could even see into the future. That is, like, we're going to say, take your online input that your algorithm is not allowed to see the entire input as it's making its decisions, and compare that to the best algorithm that could see the whole input and then could actually just work and run knowing what's going to happen in the future. And what you want to compare is you want to compare your algorithm to the best algorithm that could see into the future. Does that make sense? And this is a worst case analysis, because what we're going to do is, as we're going to define, the competitive analysis is the worst case ratio between you and the best algorithm over all inputs. Okay, so we're still in the worst case analysis, but we are comparing the worst case against the best algorithm. It's not an absolute measure anymore. Does that make sense?
Well, we're measuring at like when all the inputs are finished, right?
Exactly. We measure as all the inputs are finished, and I'm going to show some examples. Okay, so this is just the intuition. So maybe you're right. right? And here, the idea of competitive analysis is kind of saying, you know, we have an algorithm that we can't see into the future, but we know that hindsight is 20/20, right? So if we could see into the future, let's say that use the optimal algorithm, we want to be as close to having this hindsight as possible, because that would be like, oh, we made kind of closed the best decision that we could possibly have made, right? Or all the decisions that we could have made. Does that make sense? Okay, great. So, all right, so now we have this motivation. And here I just want to pause for a second and also mention that this is not the only setting for like where the input comes online, where you cannot see the input and still need to make decisions, right? So we're going to see other online models in class. Okay, so in particular, we're going to see the data streaming model, which is lecture 20. And in this case, we not only receive the input in an online fashion, as we're discussing now, but we also have memory constraints. So we cannot even store the entire input that we have seen up until the end, right? So we have very little memory, okay? And here the goals are completely different, so I'm gonna discuss that in lecture 20, okay? But today, we'll only see algorithms which must deal with the input as it receives, and we have no constraints in memory, okay? We have, well, in practice, we have a constraint in like the running time of each operation, right? So we would like the algorithm to be really fast, because once I receive the information, we would like the algorithm to have a very simple rule to make a decision, because the next information can come very quickly. But in theory, right now, we're not going to care about that so much, okay? About the running time after every time you receive an input. But you'll see that usually the running time is small, okay? But here we have no constraints in memory or running time, right? And the goal here is, again, to be competitive against any offline algorithm. And what is an offline algorithm? Well, it's the ones that are not online, the ones that can see into the future, right? That can see all the input, okay? And again, you should remember that this is a worst case analysis, yeah? All right, so let's define mathematically competitive analysis, right? So your input sequence, your input is given as a sequence S of events, okay? So each of these SIs, they're going to be events, okay? So for example, if you're trying to guess the weather, what would be your input? Well, your input would be the daily weather, right? Which comes as the day kind of arrives. And then let's say, you know, SI can be 0 or 1, and 0 if it's not raining, and 1 if it's raining, right? And then you're trying to make a decision whether to take an umbrella or not, right? That's, for example, an online problem, right? All right. And all right, what we're going to do now is, given this input S, let's say that COPT, okay, is the minimum cost that any algorithm, even one that could look the entire input beforehand, could achieve for input S. So usually, as we're saying, think about this online setting as, okay, if it's raining, I want to take an umbrella and I'll be really happy, right? And then let's say my cost here is 0 because I'm really happy, nothing bad happened to me, right? But then if I don't take an umbrella, then well, I'm going to be upset because I'm going to be all wet. And then let's say this has a cost 10. This cost me 10 because I have to change clothes or whatever, right? So here, like COPT is the minimum cost that any algorithm could, like, even when they could look at the entire input, could achieve for input S. So in this case, if you knew the weather pattern, you know when to take an umbrella or not, right? So then your cost here, let's say, would be 0, right? And now, if you have an algorithm A, so A is our algorithm, we're going to say that CA of S is the cost of your online algorithm on input S. Does that make sense? So in our rain event, it's kind of like the number of times that you didn't take an umbrella, that you took an umbrella, that you didn't take an umbrella, it was raining, right? Or let's say you took an umbrella and it wasn't raining, so you're carrying it around. So that also has a bad cost, let's say 1, right? The inconvenience. Does that make sense? So now we're going to see, we want to compare CA of S in input S to COPT of S. Does that make sense? And now what we say is that there's a deterministic competitive ratio. So if your algorithm is deterministic, Okay, so a deterministic online algorithm A. We say that it has a competitive ratio K, and we're also going to say that this algorithm is K competitive if for all inputs S, okay, so here's the for all inputs S, so that's our worst case appearing here. What we have is that the cost of the algorithm A on input S is less than or equal than K times the cost of the optimum for S plus some constant. Does that make sense? Okay, and this constant here is for some technical reasons, okay? So, all right. And now, if you say, well, but what if we want to use randomized algorithms, right? If we want to use randomized algorithms, then we say that a randomized online algorithm has competitive ratio K if for all input S again, what we have is the expected cost of your algorithm A on input S is less than or equal than K times the cost of optimum over S. Does that make sense?
Where did the O of 1 go?
Yeah, like the O of 1 here is not needed because you have these expectations, so this kind of vanishes, okay? That's why, like, it's just for some technical reasons, so you shouldn't bother too much about it, okay?
But like adding it wouldn't change the result. Like adding it would still give equivalent definitions.
Yeah, pretty much. So yeah. Okay.
Right.
So all right. So okay. So we have the deterministic and the randomized competitive ratio. Okay. So are those definitions clear? Okay. So great. So now let's go to the third part where we actually see some examples, right? So let's see how this plays out. So, okay, let's talk about like the very famous problem of ski rental, right? So, okay, in pandemic times, you know, I'm stuck in Canada and, you know, UWaterloo just gave us this 1 extra week of vacation in January 2021. So that was great. And so, you know, we decided to go skiing this past winter since, you know, we could not go back to Brazil and enjoy the beach in the summer. We're like, okay, let's go skiing. Right? Well, I mean, one could technically go, but you know, in January you really didn't want to go to Brazil. So, all right. Now we also know that the winters in Canada are very long, right? So we may go skiing a bunch of times, right? And we know we're stuck here, right, until all the way through the end. And all right, having never skied before, what do? We decide to buy. We have to decide whether we buy all the skiing equipment or if we just go to a resort and rent the equipment there, right? So that's the real problem. The real problem, I was like, okay, should we buy all the equipment before or should, you know, we rent at the resort? All right, so here's the costs, okay, the fictitious costs, right? So buying the entire equipment cost us, let's say, 1,000 Canadian dollars, and renting at the resort would just cost us, let's say, 100 Canadian dollars per day that we ski, okay? And now, well, what is the question? The question that we want to answer is that should we buy or rent? Okay. So, all right. And well, of course, the answer to this question, it really depends on how many times we'll go skiing, right? So, all right. So if we, all right, so this is the current situation. And notice that this is an online algorithm because every time we go skiing, right, we have to decide whether to buy or to rent. So what is our stream of events? Our stream of events is 0 if we rent or 1 if we buy, right? That makes sense? So, all right. And what is the cost? Well, the cost, as you can see, is the total money that we're paying, right? So it's pretty intuitive what the cost is. All right. So what is the strategy, right? Let's think about it. If we go skiing 9 times or less, okay, and we see that, okay, yeah, skiing is not for us. We're made for beaches and tropical islands, right? So then clearly it's better to rent because then we pay less than what we will ever use in our entire lives. But if we go skiing at least 11 times, and then we surprise ourselves, oh, okay, like, you know, I can deal with the cold even though I'm from Brazil and I actually like skiing, then it's clearly better to buy, right? But we don't know that in the future because we haven't gone once yet. So, all right. And if we go 10 times, it doesn't matter which way it goes, right, in our lives, right? Let's say that there's no cost for storaging or whatever. Okay. So, all right. So how is this an online algorithm? Like this discussion that we like that we just had, right? Like, how is this an online algorithm? Well, the online algorithm will be as follows, okay? Each time we go skiing, we have to decide whether to buy or rent, unless we already bought beforehand, because if we bought beforehand, we don't need to rent anymore, right? So the algorithm, the only thing the algorithm has to do is has to decide when to buy for this problem, right? Because the sequence of events is every time we go to the ski resort, right? And every time we go to the ski resort, we have only one question. Shall we rent or buy? But once we buy, that's it, right? So all that the algorithm has to do is to say, when are we going to buy, right? All right, and what does the algorithm know? The algorithm only knows how many times I went skiing before, right? That's our decision process, right? All right, so, okay, if you remember the cost, right? So these are the costs, and now let's describe the algorithm. So here's a 1.9 competitive deterministic algorithm, okay? What does the algorithm do? Well, if T, and T is the number of time, is the current time that we're going skiing, right? So if T is less than or equal to 9, then we just rent, right? And when T is equal to 10, we buy. Does that make sense? So this is the entire algorithm, right? Because after, you know, if T is greater or equal to 10, I already made my decision. Does that make sense? Okay, now let's analyze and prove that this algorithm is 1.9 competitive. Well, okay, what are all the inputs? Well, the inputs is the number of times that we go skiing, right? So if T is less than or equal to 9, then the best strategy is to rent, right? So what is the cost? The cost here is the cost of our algorithm will be 100 times T, because we just rented all these times. And the optimal algorithm that knew like how many times I'm going to ski, right? So T here is the how many times I'm going to ski. Let me just put here like T, like number of times we will go skiing, right? So, all right. So if T is less than or equal to 9, we're going less than or equal to 9 times. Then the optimal strategy, the one that already could see into the future and say, Rafael, you're only going skiing 9 times, or at most 9 times. The best strategy is just to rent. So in this case, our cost CA over COPT is 1, right? But remember, the competitive analysis is a worst case algorithm, right? So this is only for certain types of input. Now, if T is greater or equal to 10, and we buy at the 10th time, what is our total cost? Our total cost will be 100 times 9, right? Because we rented the first 9 times, and then we buy, which is 1,000. But the optimum knew that we're going to go skiing like over 10 times. So what is the cost of optimum? We might as well just buy in the first time. Does that make sense? So for these inputs, the cost of our algorithm is at most 1.9 times the cost of optimum. Does that make sense? So, all right. So what we showed here is that for every input sequence, right, which is the number of times we'll go skiing our entire lives, right? Like T equals number of times we go skiing in entire lives. Oops. Entire life is exactly, we know that CA of T is always less than or equal than 1.9 COPT of T. Right? So therefore, we just proved that this algorithm is 1.9 competitive. Does that make sense? Okay, great. So now, let's talk about the dating problem, right? This problem is also known as the secretary problem, but I really don't like that name. So I prefer the dating problem. It's more fun, right? So, all right, what is the dating problem? In the high-tech life, okay, and we're all in the pandemic, right? So you need to find someone. So you decide to join a dating site or a dating app, right? And there are n people that are interested in dating, okay? And you'd like to date the best person out there, okay? So, and here are some assumptions that we're going to make, right? So this is, after all, a math and computer science course, so we have to make some assumptions. So the assumptions here, which are terrible, but we're gonna make it anyways, is that people are comparable and that we also know how to compare two people, right? That is completely unrealistic, but let's just make those assumptions for now. All right. And all right, but you don't know who the best person is in advance because you haven't met yet these n people that you're interested in dating, correct? So you don't know who the best person is. You just know that the best person's out there. Again, disclosure, disclaimer, these are terrible assumptions, don't follow this, okay? All right, so here's one way to do it, right? One way to do it is that you could go out with all of them at the same time, right? And again, also we can assume here that they will all want to date us, right? That's also an assumption that's completely unrealistic, right? And
Especially for Waterloo students.
all right, I will silence myself here. I will not comment on that point, but okay, right? So exactly. So there's another. All these assumptions are bad, but let's just make them, right? So we'll go out with all of them at the same time, and we just can figure out which one is the best, right? But okay, this is not possible, right? Because, well, two things. Time constraints, right? You cannot go out with all of them at the same time, and also society's value system, right? Because if you're going out with many people, then maybe the person that you want to be with, the person will be very upset that you're going out with multiple people at the same time, and then that may end up very badly, right? So it's not possible to do the strategy of going out with all of them at the same time, right? All right. So okay. So what we have to do is we have to go out with one of them at a time. And then we decide whether we want to stay with them or date another person, in which case we must break up, right? And here there's no coming back together or whatever. Once you break up, it's gone. You'll never see that person again, okay? Let's just also make it simple. Life is, as you know, a lot more complicated than that. But all right, so here's our setup. We were going to go out with one person at a time and we decide whether we want to stay with them or another person. But if we break up, we cannot go back, okay? All right, so this is clearly an online setting, right? The pun is clearly intended as well. And now, what is the goal? The goal is maximize the probability of dating the best person, right? Because you want to date the best person out there, but we want to maximize the chances of that happening. Does that make sense? Okay. All right, so let's formulate this problem, right? So let's consider the following algorithm. Okay, so we already know what the problem is, right? So the stream of events is your dates, right? So you have n dates and you have to go, n in advance, but you don't know the order in which your dates will come, right? Like if the best date will be the first one, or you don't know that, right? So you know the number of dates in your life, which is also an incredibly bad assumption, but you know this number, and what you need to do is to make a decision when you're going to settle with a person, right? So here's the following algorithm. So we're going to assume that all the people we want to date are ranked, and we're going to associate them with the rank. And as two people are unique, right? No two people are the same, neither is your rank. So you know that all these people are clearly ranked against each other, and there's no ties. Right, so we know the number of people, and we know we're going to associate them with a rank, like 1 up to 2 up to n. And now, okay, so let's say, and you know their contacts, right? So let's say that you also know kind of all these people, and you just have to decide the order. So what do you do? Well, what you do, here's the algorithm. You're going to pick a random order for the n people, and let's call this order pi. Okay, because pi is for a permutation of all this 1 up to n, right? Is an order that you're going to date. And what you're going to do is you're going to flat out go out with n over e of these people. Okay, you go out with them, you date them, and then you break up with them. You just break up with them, and you'll say like, okay, it's not about them, it's about you. You haven't seen enough, you're too young to commit. You're going to use all the possible excuses in the book. but you have to break up with them, okay? N over E. And then after you go on N over E dates, you say, no, I'm a mature person now, like it's time for me to commit and settle, and now I'm ready to find the best person out there. What you're going to do is you're going to go on dates and you're going to decide to settle if the person that you found is better than anyone else that you've dated before. Does that make sense? So you built this N over E dates of experience, and now you know how to compare. And now if you say that someone is better than everybody else that you've seen before, you'll stay with that person. Does that make sense?
For step 2, is it possible to pick anything other than a random order? Like if we don't really know anything about them yet?
Well, it is, but then, random order has the advantage that, if you don't know them, in the worst case, you could go out with the best person right away, and then you ditch that person, and then,
Right, I'm just saying, like, we don't really know anything about them, like, at the beginning, like, at step 2. So I don't think it's possible to build, like, any order other than, like, just shuffle.
Well, I mean, yeah, what I'm saying that it is, right? Because you can choose the order, but you're right that I think what you meant to say is that if you don't do it random, if you do it deterministically, then there's a worst case input, and then you're going to be lonely, right?
Yeah.
I think that's the more precise way to say it, right? Because you choose how to date. I mean, who am I to tell you, right? But I agree. Random decreases the chances that this will go bad. Right, and it's a usual principle as well in algorithms, right? Like whenever we don't know what's coming at us, we kind of operate randomly, right? So, okay, great. Yeah, it's great observation. Yeah, that's a great observation. I should have pointed out more why we are picking a random. All right, so here's the claim, okay? This algorithm will pick the best person, the one ranked 1 in your list with probability 1 over E, okay? So, and remember, here we're going big or going lonely, right? So either you're dating the best person or you're not, you're going to end up single for the rest of your life, right? So this algorithm gives you a probability of 1 over E to find the best person out there, right? So it's the high risk, high reward dating game. All right. So again, so there's a more general algorithm, but we're not going to analyze this because this is just a simple example. Okay, what you can do is given a time t, you go on t dates, and from date t plus 1 onwards, you decide to settle with the person who's better than the previous ones, right? The algorithm that I just described is just the algorithm where the t is equal to n over e. Okay, that's all. I already picked this parameter t. Does that make sense? So t is the level of experience that you want to have before you commit. Okay, so, all right. So now, given this algorithm that we're talking about, right? What is the probability that we pick the number 1 in our list, right? Like the best person out there. So, all right. So let's start analyzing this problem. Suppose that we pick a person at time t, at time k, okay? So that's when we pick the person. That's when the algorithm told you, like, I will pick the person at time k. What we want to compute is the following probability, the probability pk, of the probability that the kth person is the first person, right? Because you're picking the person at time k, right? Like that the first person shows up at time k, and that we also pick the person at time k, right? Those two things have to happen for us to pick the number 1 at our list at time k. All right, so what is our final success probability? Our final success probability will be exactly the sum of all of these pk's for k bigger than t, because remember, we're looking at this algorithm that given the time t, I'm going to reject flat out anyone that came before t, and only I'll decide to settle from t plus 1 onwards. Does that make sense? So our probability of success is exactly the sum that I will succeed in one of the steps from t plus 1 up to n. Okay, so if pi of k is equal to 1, okay, then we have here that 1 minus pk is the probability that we pick the person between t plus 1 and k minus 1, correct? because if we already know that the best person is at position K, what is the probability that I fail? Probability that I fail here is the probability that I have to pick a person before I see the first person, right? So this is the probability that we pick the person between times t plus 1 and k minus 1, right? Which means that someone in this range is better than the first t people that we saw, because that's our algorithm. Does that make sense? So here, what do we know? We know that pk will be what? Well, be the probability that pi of k is equal to 1. That was already in the definition. And we didn't pick anyone before, right? So this will be, we did not pick anyone before k. Before time k, right? Or date k, I guess. Now, and what is this? Like, we didn't pick anyone in date k, like up to before date k, mathematically. Well, mathematically, what is our algorithm doing? Our algorithm is going to say, well, remember, the best rank is the smallest rank, correct? That's the best rank. So the only way our algorithm is not going to pick anyone before k is if the minimum of the ranks of all the dates that we had. So these are ranks of all dates up to date k minus 1. This minimum, the best person up to step k minus 1 was actually in the first t people. Does that make sense? Because if I saw the first person, like the best person in the first k minus 1 dates within the first t, I know I'm going to flat out reject this person and I'm not going to see anybody better until I see the best person. Does that make sense? Okay, now let's compute this, right? So we know the final success probability will be pk. And all right, from this previous slide, what do we have? We have that pk is the probability that the first person is at position k. What is the probability that this event happens? This probability is exactly 1 over n, right? Because I took a random permutation. So if I take a random permutation, what's the probability that position k will have the number 1 person? It's exactly 1 over n, right? And now, what is the probability that the minimum of pi 1 up to pi k minus 1 is within the first t positions? Right? So here it's just quite simple, is you just look at all the permutations and you look at all, like the first sequence of k minus 1 elements, right? So if you look at all the sequence of k minus 1 elements, or maybe, yeah, let's analyze this probability. So this is equivalent to just saying, like, picking a permutation of 1 up to k minus 1, right? Let's suppose that within the first k minus 1, we have like some, they have different rankings, so we can assume just that they are like 1 up to k minus 1. What is the probability? Like such that 1 appears within first t places, right? Because 1 is your best ranked person, right? Here, maybe if you're confused, we can replace 1 up to k minus 1 to say like A1, A2, all the way up to a k minus 1, let's say. These are the rankings, and what you want is the A1 person to appear within the first t places. Well, if you pick this permutation at random, right, what do you have? You have t locations for the first person, for A1, over all the k minus 1 locations. Once you pick that, you're good. So this is exactly the probability of the minimum being within the first t places. Does that make sense? So this is our probability of success. So if the probability that the first person will be at location k, and that we're not going to pick anyone until we see that person, is exactly T over N times K minus 1. Okay. And now what do? What we do is, well, a success probability P will be equal to the sum for all K bigger than T, right, of 1 over N times T over K minus 1, right? But if you notice, well, T is a constant and N is also a constant, right? So those two are constants. They don't depend on K, and this sum is summing over K, right? So then we can extract T over N from the equation, and then we have the sum of 1 over K minus 1 from K going from T up to N, right? But then we know, right, by the harmonic series that this is exactly equal to like log N T minus log N N. So then what we have is, in the end, our probability of success will be T over N times the natural log of T over N. Does that make sense? Okay. And then if we optimize this, we see that we should actually set T to be equal to N over E, which gives us a 1 over E probability. Does that make sense? So this would be our probability of success. But now, if you're paying attention to all that we talked about, you're going to ask, wait a second, but this is not competitive analysis. Like, where is the competitive analysis? This is not competitive at all. You just gave me an algorithm and you gave me a guarantee. And indeed, you will be right. So how do we make dating competitive, right? So that would be your question. How do we make dating to fit in this framework? Well, to make the dating problem competitive, we would just have to modify it a little bit. And how do we modify this problem? Well, we can simply say, instead of picking the best person, right? What we can say is we want to minimize the rank. So the cost of your algorithm is the rank that you end up with. Does that make sense? So you see all the people, and then once you decide to settle, the cost that you're paying is the rank of the person that you're gonna end up with, okay? And we wanna minimize this rank, right? That's the whole goal, is to have the rank as small as possible. All right, so, and now, let's also just assume that we always want to end up with someone, that loneliness has a cost of minus infinity. So after all, nobody wants to be alone, right? So let's say that if you date everyone and you haven't made a decision until your last date, that last date, that's it. You're committing, okay? All right. So what would the previous algorithm do? The previous algorithm would either pick the best person or the last person in the order, right? Like, so not the last in the ranking, but not necessarily the last in the ranking, but the last person in the order. Does that make sense?
Wait, so the input, what was the input for this?
So the input will be exactly the sequence of like a permutation of the ranking, right? So you have N people, you know N, and so does the optimum. And the only thing is, but you don't know, like, you don't know how the ranking is going to be distributed, right? How the ranking is going to come at you.
So can we like think of it as like, say we have the first K people, and then when a new person comes, you're like, well, here's where they fit within the previous K people, not the rest of it. Because if you got the actual rank number, it'd be trivial, right? You just stop when you hit 1.
Oh yeah, exactly. We know. Yeah. Oh, good point. Sorry. Let me make that clear. Excellent question. The setup here is that all you know beforehand, let me clarify what I said before. All we know beforehand is that we know that we can rank the people beforehand, right? Like, sorry. All we know is that we know that each person, like, we can compare two people and we can say between two people, there's a better one. That we know. So in particular, we know that there's a total order in the ranking, right? So we can assume that there's this person is rank 1, this person, but we don't know who is rank 1. All we know is if I see a person at time K, all I can do is compare to the people that I have seen. Does that make sense?
All right. So we get like the comparisons. Like when a new person comes, we get at our input is the comparisons to the previous people we've seen.
No, the input is the people, right? So, okay, so let me explain here again. So the input will be the ranked people, but you don't know the rank, right? So it's a sequence of people.
Oh, so it's kind of like encapsulating a rank within the object, but like you can't look at the rank.
Exactly. So
Okay.
the sequence of people, you have person 1, person 2, all the way up to person N. And hidden from you, you have the ranking, right? Like the ranking of person 1, ranking of person 2, and ranking of person n. Now, the thing is, all you know is the rank function, right? Like, you know the ranking function, which goes from the people like n up to n, right? Like, you can rank them.
Right.
But you don't know actually. So, sorry, you know that, how do we say?
We have like a comparison function between like two people.
Exactly.
And
we know that this exists, but we don't know, right? Like, we don't know it.
Right. So we have access to a comparator, but not the index value.
Exactly. So all we can do is a comparison, like comparison between person I and person J tells me which one is the best.
Cool.
Okay, and maybe, yeah, if I do mathematically here, if I just want to write like more formula, you're gonna say like the minimum outputs, like the arg min, right? Like the I or J, like arg min between the rank of PI and rank of PJ. Right? It will output me like PI if the rank of PI is smaller, or PJ if the rank of PJ is smaller. Does that make sense?
Yep.
Okay, great. Excellent question. Yeah. So this is what we were doing before, right? The only thing we can do is we have this comparison, right? So, okay. And all right, so our algorithm, right? We would either pick the best person or the last person in the order. Okay. All right. So here's the thing. We know, okay, like it's an easy probability question, right? That with constant probability, the rank of the last person is omega n, right? So the algorithm that we described before, we either end up with the best person or we date someone in kind of the bottom percentile of our list, right? So those are the events that will happen with constant probability, right? So we either going to end up like with probability 1/e, we're going to end up with the best person, or with some other constant probability, we're going to end up with a person that's ranked like in the bottom half of our list, right?
Why do we pick the best person or the last person?
Because our algorithm works like that, right? Suppose that if the first person appeared within the first like n/e slots, then we're going to reject everybody until the last person, right? Because every time that I look at it, I'm like, oh, I already saw the best person in my life. The love of my life was there. I don't want to date you, right? Like that would be that's what the algorithm is doing.
But if the best person does not appear, then we can pick then the person we pick need not be the last person.
Correct. But exactly. So there are 3 cases, right? So either the first person appears and then we're sure to pick the last person, or the best person didn't appear in the beginning, and then it appeared later, but we picked someone without seeing who the best person was.
Yeah.
Right. And all I'm saying is that this also has some probability of happening, right? But all I'm saying is that there's a constant probability of getting the best, and there's a constant probability of getting the less, which is bad.
Oh, okay.
That's all I'm saying.
Okay.
Yeah. So yeah. So there's and why am I saying this? Is because if you think about it, now we're in the randomized, setting, right? Like the randomized competitive analysis. So if we get with constant probability a person of rank omega n, then we have a lower bound on the competitiveness of our algorithm, right? Because what is the expected cost of our algorithm? Expected cost of our algorithm will be exact on, let's say, suppose that we have an input S here, right? So the expected cost of our algorithm here, well, we know that with constant probability, we're going to stay with the last person. So this is equal to omega n, right? Because this expectation is greater or equal than the probability that we end up with last person times the value, like the, like the rank of the last person. And we're saying that if we pick the input at random, there's a constant probability that this guy is going to be omega n, and this is constant. Does that make sense? So that's all I'm saying, is that this bullet, right, is just saying that this algorithm is not very good, because now with this algorithm, what is my expected competitive cost? My expected cost here is going to be omega n, right? Does that make sense? And now here's the thing, right? So the expected rank of our lifelong partner is omega n, as we just saw, but can we do better, right? Because the thing is, what is, now let me add another bullet here, and then we can answer this question together. What is the best algorithm do? What is the cost of optimum over S?
Is it just one?
Exactly. It's just one, because opt can always see in the future. In the future. So in particular, like just to go back to what Joey was saying, we know that opt, we can just say that opt knows R, the rank function. So opt will always, you know, say, okay, you're not the best. I know the best will come. And then once the best person comes, like, okay, yeah, you're the best. I'm going to end up with you, right? So this algorithm, what is the competitiveness of this algorithm? The algorithm that we just talked about in this online setting is omega n competitive, which is pretty bad because we have like n people, right? So can we do better? The question is, can we do better with an algorithm? And the answer is yes. Okay. And it's actually funny, it's satisfyingly more intuitive. It is very intuitive, right? So there's an algorithm that picks a person of average rank O of 1. Okay. So there is an O of 1 competitive randomized algorithm. Okay, and what is this algorithm? It's a very complicated algorithm, actually, and it's based on computing time steps like T0, T1, and so on. And here's what the algorithm will do. Between time steps Tk and Tk plus 1, think of this as milestones. Between Tk and Tk plus 1, what we're saying is we're going to relax our condition, and we're going to say we're willing to pick the person who is at most the k plus 1 best from our current list. So not just the best, you know, let's say between T0 and T1, right? We're going to say we're only picking the best. We're very picky. But then T1 passed and we're getting older. We're like, okay, maybe I already saw the best. Maybe let's go for the second best. And then you give yourself a timeline and you say, okay, between T1 and T2, I'm going to pick the second best person that I've seen. Does that make sense? And you have to compute these time steps to optimize all of this. Right? So the algorithm is a little bit complicated, but is encapsulating exactly this intuition that, oh, as you get older, we become more desperate to find someone. So what do we need to do? We need to lower our expectations, right? So it turns out that this algorithm is O of 1 competitive, which is pretty good. I mean, pretty good compared to all the terrible assumptions that we have made, right? So, so if you believe on those assumptions, then you can certainly use this algorithm and you'll do like O of 1 competitive to the best you could do. But again, those assumptions are pretty terrible. Does that make sense?
And this kind of encapsulates like every possible reasonable algorithm, right? Like you wouldn't want to say if it's better, if it's like better than all of mine. I mean, it's like I'm only going to pick it if it's like the second best and not the best compared to everything you've seen before, right? Like it kind of encapsulates all of it, and you wouldn't want to become less picky. I mean, you would not want to become more picky as time goes on. Right.
I don't know, right? The whole problem is it's really hard to prove that that's not better. Does that make sense?
I mean, intuitively kind of makes sense.
Oh, intuitively, a lot of things make sense. And you're right.
Yeah.
And intuitively, I will agree with you, right? But if you want to prove that that's worse, then I don't know how to do it.
I see.
Okay. So I just want to make that distinction, but I agree with you. The intuition would lead to this being the best algorithm, right? But again, it's an intuition. All right, sounds good. All right, so then this is the first part of the lecture, and now let's talk about some actual computer science problem with great assumptions.